Energy production and use have a big impact on our environment. Problems like solid waste, air pollution, water pollution, heat pollution, and climate change all connect to how we generate and consume energy. One major cause of these issues is burning fossil fuels. When we burn fuels like coal, oil, and gas, harmful substances such as black soot, also called black carbon, and greenhouse gases are released into the air, polluting it. Water bodies are also affected, especially during oil spills from extraction and transportation. Coal mining can harm water quality because minerals from the mining process can leak into nearby rivers and lakes. Because of these problems, people have been searching for cleaner and better ways to produce and use energy. Hydrogen has emerged as a promising clean energy source. Hydrogen is the most abundant element in the universe, making up about 74% of all atoms. It usually bonds with other atoms to form molecules, but as a fuel, hydrogen itself offers great potential. A former US president once mentioned that cars running on hydrogen fuel would produce only water as exhaust, meaning no harmful emissions. Research confirms that hydrogen is a very clean fuel. Despite these benefits, there are still challenges in adopting hydrogen widely. One big challenge is how to store hydrogen safely and efficiently. Hydrogen gas is very light and has a low density, meaning it takes up a lot of space. For vehicles to drive more than 300 miles, they need to carry a lot of hydrogen, which means the storage system needs to be compact, but also safe. This makes hydrogen storage a key issue to solve. Hydrogen is mainly produced from fossil fuels like coal and natural gas, which make up about 60% of the world's hydrogen supply. This means most hydrogen is made in special facilities designed just for hydrogen production. Only a small amount of hydrogen is created by splitting water through a process called electrolysis. However, hydrogen made this way often needs extra cleaning, like removing water or other impurities to make it pure enough for use. Most hydrogen today is produced close to where it will be used. Around 75% of hydrogen worldwide comes from natural gas. Each year, about 70 million tons of hydrogen are made from natural gas, which requires a large amount of natural gas, around 6% of the global supply. This hydrogen is often produced using a method called steam methane reforming, especially for industries like ammonia and methanol production, as well as for oil refineries. Steam methane reforming uses natural gas and water to produce hydrogen. There are different ways to do this, using water as an oxidizer, using oxygen from the air, or combining both methods, which is called autothermal reforming. Hydrogen can also be made from other fuels like liquefied petroleum gas and naphtha through steam reforming. Besides natural gas, heavier fuels like heavy fuel oil and coal can be used to make hydrogen through a process called partial oxidation. Hydrogen storage plays a crucial role in the future of clean energy. Hydrogen is seen as a key part of the move towards sustainable energy because it can help reduce the pollution caused by traditional carbon-based fuels. It offers a clean way to produce energy, especially when used in hydrogen fuel cells. These fuel cells can power a range of devices from small electronics to vehicles like cars and airplanes, as well as infrastructure. One of hydrogen's biggest advantages is that it can be stored in large amounts for a long time, something batteries can't do as effectively. This makes hydrogen an important backup energy source when needed. In transportation, hydrogen can work alongside batteries, offering extra fuel support. However, to fully embrace hydrogen as a major energy source, more research and development are needed, especially in building the infrastructure and improving storage methods. For example, a typical utility company, along with government programs like the Hydrogen and Fuel Cell Technologies Office, is working hard to develop safer, more efficient ways to produce and store hydrogen for everyday use. Hydrogen storage can take different forms. It can be kept as a gas or liquid, or stored inside solid materials like metal hydrides, cylinders, balloons, or glass microspheres. Each method has its own benefits and challenges, such as cost, weight, safety, ease of use, and how much hydrogen it can hold. Metal hydrides, for example, are considered one of the best options because they can safely store large amounts of hydrogen in a small space. However, these materials can react with water or alcohols, sometimes creating unwanted byproducts. Glass microspheres are an exciting new option in hydrogen storage that shows promise, but more work is needed to improve the technology for making and using them effectively. Storing hydrogen safely and effectively comes with many challenges. Like all fuels, hydrogen's risks depend on factors such as how much fuel is present, the availability of oxygen, and possible sources of ignition. To reduce these risks, proper engineering controls and safety measures are essential. Hydrogen behaves differently from traditional fuels because it has a very low density, spreads quickly in the air, and burns with a flame that is almost invisible. This means that leak detection and good ventilation are very important when working with hydrogen. Although hydrogen is highly flammable, it also has some safety advantages. For example, hydrogen is not toxic, and if a leak happens, it disperses quickly into the atmosphere, reducing the chance of dangerous buildup. However, it still requires special safety equipment like flame detectors designed specifically for hydrogen because its flame is hard to see. It also takes less energy to ignite hydrogen compared to fuels like gasoline or natural gas. Choosing the right materials for hydrogen storage is another challenge since some metals can weaken or become brittle when exposed to hydrogen. Because of these issues, handling hydrogen in high-pressure tanks requires skilled and trained personnel. This has led researchers and engineers to explore safer, alternative ways to store hydrogen. One method involves storing hydrogen underground in places like old oil and gas wells, salt caverns, or underground water reservoirs. While this underground storage is effective, it is also expensive and not widely used yet. Most existing underground hydrogen storage facilities are in Europe and the United States, often using depleted natural gas fields to hold hydrogen generated from renewable energy sources. Hydrogen itself is tricky to store because it is the lightest gas, has a very low boiling point, and can easily escape into the atmosphere due to its reactive nature. Its density is much lower than natural gas or gasoline, which means storing enough hydrogen requires compressing it to very high pressures, cooling it to liquid form at extremely low temperatures, or chemically combining it with other materials. All these methods come with technical challenges and costs, but they are necessary to safely contain hydrogen for future energy use. When it comes to storing hydrogen efficiently, no single material has yet met all the necessary requirements. For example, palladium can absorb and release hydrogen at low temperatures, but it can only hold a small amount less than 1% by weight, and it is very expensive, which makes it impractical for wide use. On the other hand, a complex material called Li3Be2H7 can store a much higher amount, about 8.7% hydrogen by weight, and it can release and absorb hydrogen repeatedly. However, it is toxic and works best up to temperatures around 300 degrees Celsius. Another material, aluminum hydride Al3, is very efficient in storing hydrogen about 10% by weight and uses aluminum, which is relatively cheap. But most of the hydrogen stored in this material is released in a way that cannot be reversed, limiting its practical use. Sodium borohydride NaBFOR dissolved in water can store about 9.2% hydrogen by weight, and with the right catalysts, hydrogen release can be controlled well. Still, recovering the original material after use is difficult. Pure water itself contains hydrogen about 11% by weight, but breaking it down to extract hydrogen requires a lot of energy, either heat, electricity, or chemicals. More recently, materials like nitrides and amides have shown promise by storing 6.5 to 7% hydrogen by weight at higher temperatures near 300 degrees Celsius. In addition to these materials, Hollow glass microspheres (HGMS) have attracted attention for their ability to safely store compressed hydrogen gas. However, HGMS have poor thermal conductivity, which means they release hydrogen slowly when packed together. To improve this, scientists have experimented with monolithic glass plates that contain small amounts of elements like iron oxide Fe3O4. These doped glass plates can release hydrogen faster when exposed to infrared light. Research shows that radiation from infrared lamps can speed up hydrogen release from these materials, potentially making glass microspheres more effective for hydrogen storage. Microspheres are tiny spherical particles that come in two main types, solid and hollow. The hollow ones are often called microbubbles or hollow microspheres, while the solid ones are known as microbeds or just microspheres. These small materials are used in many different industries because of their special physical and chemical properties. For example, they are very light, they don't conduct heat well, they can withstand pressure without breaking, and they don't easily react with other chemicals. Today, microspheres and microbubbles are becoming more important, especially in advanced technologies like optics. They are used in devices called whispering gallery mode resonators, which help create very precise lasers and tiny sensors. Researchers are especially interested in using these microspheres in fields like biosensing, where they could help detect biological signals more accurately. Glass microspheres are tiny spherical particles that can be made from different types of materials. Usually, they are produced using special kinds of glass called amorphous materials, such as oxide and chalcogenide glasses. But glass is not the only material used to make microspheres. Many other materials, both man-made and natural, can also be used depending on the purpose. For example, microspheres can be made from polymers, which are types of plastics, or from stainless steel. These materials make microspheres useful as small parts in machines, like spacers that keep components apart, shock absorbers that reduce impacts, or bearings that help things spin smoothly. Some hollow microspheres made of metals, like nickel, have special magnetic properties that make them useful in different technologies. There are also tiny metal spheres made from combinations of metals, such as nickel and platinum, which can help create portable hydrogen production systems. Other types, like ferrite microspheres, have applications in medicine and technology. They can be used in cancer diagnosis and treatment, help separate biological molecules, or assist in magnetic resonance imaging (MRI). Some microspheres are made from single crystal semiconductors and are used in advanced optical devices called whispering gallery mode resonators. Meanwhile, ceramic hollow microspheres, such as those made from zirconium oxide, are well suited for applications involving heat resistance. On the market today, you can find many types of microspheres made from glass, polymers, ceramics, solid metals, and hollow metals. These microspheres come in various sizes and shapes, and their quality can be adjusted to fit different needs. This variety allows manufacturers and researchers to choose the right kind of microsphere for specific uses across industries. Oxide-based glass microspheres are tiny spherical particles made from pure silica or a combination of oxide materials. These microspheres are widely used in both scientific research and various industries because of their special properties. They also have many commercial uses. When scientists need microspheres with very precise qualities, such as for advanced devices like whispering gallery mode resonators or tiny coordinate measuring machines, making these spheres requires skill and careful control. One common way to make high-quality oxide glass microspheres is by melting the tip of an optical fiber. When the fiber tip melts, surface tension naturally shapes it into a nearly perfect sphere. To achieve this, different sources of heat can be used, such as electric arcs found in fiber splicing machines, powerful lasers like CO2 lasers, or even flames from torches burning oxygen and butane gases. For fibers made from multi-oxide glasses, which melt at lower temperatures than pure silica, simpler heating tools like resistive microheaters may be enough to form the microspheres. Special machines called optical fiber fusion splicers help control this process very precisely. For example, a popular model used in Tokyo carefully holds the fiber tip in place and applies a series of electric arcs. These arcs partially melt the fiber tip, allowing surface tension to shape it into a smooth, round sphere. The temperature inside the splicer can reach as high as 2000 degrees Celsius, which is hot enough to melt pure silica and form the microsphere needed for advanced applications. Glass microspheres are tiny spherical particles made from glass, often used in scientific and industrial fields. Researchers have developed methods to create very small microspheres, sometimes less than 100 micrometers in diameter. One way to make these tiny spheres is by using optical fibers. By carefully heating and shaping the fiber tips, specialists can produce microspheres with excellent roundness and smoothness. The size of these microspheres depends on the starting fiber and the heating process, with sizes typically ranging up to around 350 micrometers. Traditional methods often create a single microsphere attached to the fiber, which might not suit all uses. For other applications, it's better to have separate, loose microspheres. To achieve this, glass powder is melted and shaped into spheres using laser heating or plasma torches. These methods can produce many microspheres at once, but they often create particles with varying sizes and surface qualities, meaning further sorting is needed to select the best ones. In laboratories, microbubbles' tiny hollow spheres are sometimes attached to capillary tubes to create special devices for medical uses. These microbubbles can be formed by heating pressurized glass tubes with lasers or electric arcs, shaping them into hollow shells with openings. For larger-scale commercial use, separate solid or hollow microspheres are manufactured by heating glass powders, sometimes with additives that create bubbles inside the spheres. Glass microspheres, both solid and hollow, have grown in commercial importance. The market for these tiny glass spheres has been expanding rapidly, with estimated values reaching nearly $2 billion and steady annual growth. There are many patented designs tailored for different uses, reflecting the diverse applications and continuing demand for these unique materials. Chalcogenide glass microspheres are made mainly from three special elements: sulfur, selenium, and tellurium. These materials have unique qualities. They respond to light, have very low vibration energy, and allow infrared light to pass through them easily. This makes them quite different from many other glass types. Making chalcogenide optical fibers usually involves heating the tip of a fiber until it melts. More commonly, a vertical furnace filled with argon gas, which is non-reactive, is used to handle the molten glass. This method is necessary because chalcogenide glass can react easily when heated, so the argon protects it from unwanted chemical changes. These solid microspheres have many useful applications. They can detect tiny biological molecules, measure temperature changes, amplify light, and even help create laser beams. Beyond this, special tiny crystals made from combinations of metals and chalcogenide elements are being studied for renewable energy use. These crystals, such as copper indium sulfide or lead telluride, could help improve the efficiency of energy devices in the future. Glass microspheres, both solid and hollow, have many uses depending on their material and size. They have attracted a lot of attention, especially in the field of energy, which focuses on reducing energy use, storing energy, and producing energy. One important area is cleaner vehicles. Electric vehicles powered by fuel cells are promising because they can travel long distances on a single tank and can be refilled quickly, unlike battery electric vehicles. However, storing hydrogen safely and efficiently remains a big challenge for these vehicles. Hollow glass microspheres HGMIs are seen as a promising material for storing hydrogen. These tiny spheres range from 1 to 100 micrometers in size and have porous walls that allow hydrogen gas to be trapped inside. Researchers have found that HGMIs can hold hydrogen by letting it diffuse through their thin walls at high temperatures and pressures then trapping it when cooled. The main problem with HGMIS has been that they don't conduct heat well, which slows down the release of hydrogen gas. To solve this, scientists have experimented with adding metals like cobalt to the glass to improve thermal conductivity. For example, adding cobalt increased thermal conductivity significantly, but too much cobalt blocked the pores and reduced storage capacity. To speed up hydrogen release, one effective method uses infrared light to heat the microspheres, a process called photo-induced outgassing. By mixing glass with metals like cobalt, nickel, or iron that respond to light, the release of hydrogen can be improved. Studies show that glasses doped with small amounts of iron or cobalt respond better to infrared light, which helps release hydrogen faster. This technique offers a practical way to improve hydrogen storage and release for real-world applications. Beyond hydrogen storage, hollow microspheres are also being explored for other energy uses. Microspheres made from different materials like vanadium pentoxide or titanium dioxide are promising for use in lithium-ion batteries and supercapacitors. These hollow spheres can safely hold pressurized gases and offer a low-cost, efficient option for energy storage. HGMIS have even been studied for decades in nuclear fusion research, where they serve as tiny fuel capsules needed for laser-driven fusion reactors. These microspheres need to be made economically and with precise sizes and wall thicknesses, making them key components in cutting-edge energy technologies.